Hello YouTube. In this video I want to outline in broad brushstrokes the case for a position that I'm calling dietary nihilism. So recently Jacob Stegenga has defended a view known as medical nihilism. According to medical nihilism, and I quote, "We ought to have low confidence in the effectiveness of novel medical interventions. For instance, there are lots of ailments that we treat with pharmaceutical drugs. Stegenga argues that in the vast majority of cases, these drugs are unlikely to be effective." I'll put up a link in the comments to a lecture where Stegenga introduces this view. But it occurs to me that Stegenga's arguments might apply in other contexts. In particular, I suspect there's probably a equally compelling case for a kind of dietary nihilism. So what I want to do in this video is take Stegenga's argument about medical interventions and apply it to the case of nutrition science. All right, so what exactly is dietary nihilism? Well, the basic idea is simple. We ought to have low confidence in claims about the health effects of different types of diet, even when these claims are supported by what seems to be good scientific research. The dietary nihilist is going to say, we don't know what would be the healthiest diet. Perhaps there just is no healthiest diet. Basically, just as the medical nihilist says that we should have low confidence in medical interventions to improve health, so the dietary nihilist says that we should have low confidence in dietary changes to improve health. Now, there are very obvious limits to medical nihilism. If you take vaccines and antibiotics, these are obvious magic bullets that will either prevent or cure specific illnesses. And similarly, we have some other types of medical interventions, like insulin for treating diabetes. That is a highly potent intervention that, makes a big difference. So the medical nihilist does not claim that all of medicine is just completely useless. At least most medical nihilists aren't going to claim that. But it's a more pessimistic attitude towards medicine. It's particularly towards new medical interventions. So, what a medical nihilist will say is that, look, at this point, we've kind of we've already discovered the sort of low-hanging fruit in terms of medical techniques, and like these more sort of contemporary developments are, we should be much more skeptical of them. I mean, that's the general idea. Similarly, there are obvious limits to dietary nihilism. So just as there are some medical magic bullets, so there are some dietary magic bullets, in particular the identification of nutritional deficiencies. For instance, we know that scurvy is caused by vitamin C deficiency. You can take 100 people with scurvy, start feeding them oranges and lemons, and their condition will clear up. So, you have a potentially life-threatening illness that can be reversed within weeks. That is a striking and almost immediate improvement. Another kind of magic bullet is the identification of toxicity. If a person were eating bags of Brazil nuts every day, they'd end up with selenium poisoning. So don't do that, right? So these are the dietary magic bullets. We've identified the minimum levels of nutrients that are required for the human body to function, and we also know the levels that would be toxic. To that extent, we know what makes for a healthy diet. But of course, for the majority of people in the West, where foods are fortified and supplements are available, if you're not getting enough vitamin B12, you can get a supplement for it. I mean, nutritional deficiencies are easily corrected. People don't usually poison themselves. What we see in contemporary nutrition science is an attempt to identify the long-term health impacts of different diets that are otherwise nutritionally complete. So we want to know, what is the best diet for preventing cancer, heart disease, diabetes, and so on? You might read a study that tells you that, consuming eggs increases the probability of heart diseases, or maybe consuming almonds reduces the probability of dementia. These are the sorts of claims about which the dietary nihilist will be skeptical. So, we don't know what the ideal diet is. Maybe there is no ideal diet, and we should have very low confidence in studies which make claims about the long-term health impacts of different foods. I should say, for what it's worth, I don't myself endorse dietary nihilism. I'm just exploring what might be said in favour of it. So that's where I'm coming from here. I will upload a video to my Patreon where I explain more of my own stance. But anyway, for the rest of this, I'll be sort of speaking with the voice of the dietary nihilist. I suspect that many people will find this kind of view intuitively attractive. I mean, dietary advice seems to change all the time, right? 10 years ago, they told us that eggs cause heart disease due to their high cholesterol content. Then they told us that eggs are perfectly fine and dietary cholesterol is not related to blood cholesterol. Now they're saying that eggs are bad again, but for different reasons, whatever, right? If they were wrong before, why trust them now? The history of diet science is a graveyard of failed advice, and so probably the contemporary advice will be overturned in short order too. This kind of pessimistic induction against diet science, I think, probably captures a lot of people's attitudes. But we do have to be careful here, partly because, who is it that's telling us these things? I mean, obviously what gets reported in the media is perhaps somewhat different from what the experts are saying, and in any case, the mere fact that advice is different today might just indicate that we know better now than we did in the past. I mean, we've done more studies, we've figured out what the facts are now. We didn't know that in the past. It's not surprising that things change. But as I said, I think there is at least some intuitive pull to this sort of position. So can we give a more substantial argument? Well, Stegenger states what he calls the master argument for medical nihilism. He states this in Bayesian terms. So we're going to give similarly a Bayesian master argument for dietary nihilism. So this uses Bayes' theorem, which is a formula that allows us to calculate the posterior probability of a hypothesis given some evidence. So I've got Bayes' theorem there. Now, if you're not familiar with this, there are many places online which explain it. I actually have a video on general Bayesian epistemology, which gives some examples of Bayes' theorem in action. But you'll be able to follow everything that comes in this video without understanding exactly how this works. The key point is it's a formula that allows us to determine the probability of some hypothesis given some piece of evidence. So the probability of the hypothesis given the evidence, the probability of H given E, depends on three other probabilities. It depends on the probability of the evidence given the hypothesis, that is, the probability that we would get that sort of evidence if the hypothesis were true. Second, it depends on what's known as the prior probability of the hypothesis, basically how confident we are in the hypothesis prior to examining any evidence. And then third, the so-called expectancy of the evidence, or the prior probability of the evidence irrespective of the hypothesis. So we can use these probabilities to work out the probability of the hypothesis given the evidence. So apply this to dietary hypotheses. Take some hypothesis about diet, say that high meat consumption causes heart disease, or that eating lots of nuts reduces dementia, whatever. So we're only going to accept this dietary hypothesis if we have some sort of evidence for it, obviously. And to this end, scientists conduct studies designed to test dietary hypotheses. So we have a hypothesis, and then we have the publicly available evidence for it. Maybe this is in the form of observational studies of populations, or short-term feeding studies, or animal models, or meta-analyses of such studies, or whatever. So now we can ask, okay, what's the probability that this dietary hypothesis is true given this available evidence? And we can apply Bayes' theorem, and in abstract, the master argument basically looks like this. So for any given dietary hypothesis, H, the probability of the evidence given the hypothesis is low. So even given that the hypothesis is true, there is a low probability of observing the evidence in question. The results of the study are not made significantly more likely by the truth of the hypothesis. Second, the prior probability of the hypothesis is low. Prior to examining a study on the hypothesis, we should have low confidence in the hypothesis. And then third, the expectancy of the evidence is high. So the sort of probability of observing the evidence that favours the dietary hypothesis is high regardless of whether the dietary hypothesis is true. Now, it follows from this that the probability of the hypothesis given the evidence is low. And obviously this is all rather abstract at the moment, but we will fill in the details and hopefully things will become much clearer. The point is just this: if we can establish these three claims, right, if we can establish that the probability of E given H is low, the probability of H is low, and the probability of E is high, if we can establish those three claims, then we can infer that the probability of H given E is low. In which case we should have low confidence in H. The evidence that we have is not actually good evidence for H. So we should have low confidence in the dietary hypothesis, even given these studies that seem to confirm the hypothesis. So now the obvious question is, well, how do we defend these premises? Let's start then with the probability of the evidence given the hypothesis, right? So the claim is that the probability of E given H is low. This is the probability that you get this evidence that you have in fact gotten, given the truth of the hypothesis. Why is this hypothesis low? Well, there's a couple of reasons. So first of all, one problem here is that the vast majority of dietary interventions have very small effect sizes. The harmful effects of particular foods, or the benefits that are claimed for particular foods, are almost always very small. So basically, right, what we're asking here is we take some dietary hypothesis. The question we're asking is, would we see evidence like this if the dietary hypothesis in question were true? And so it's worth comparing this with like an ideal case, such as the association of smoking and lung cancer. So in this case, we have a hypothesis: smoking causes lung cancer. We can then examine smokers and non-smokers and see what their cancer risk looks like. It turns out that the lifetime risk of lung cancer for a smoker is over 20%. The lifetime risk of lung cancer for a non-smoker is less than 0.5%. That is a remarkably clear effect, and it's replicated across many, many populations. Unfortunately, and of course, this sort of effect, that's exactly what we would expect to see if the hypothesis were true. Unfortunately, we don't see effects like this for dietary hypotheses. So let's take an example. So according to the World Health Organization, if the link between red meat consumption and colorectal cancer was shown to be causal, then the risk of colorectal cancer would increase by about 17% for every 100-gram portion of red meat eaten daily. You can find different numbers in different places, but that's what the World Health Organization says. So we'll take this as an example, right? So yeah, 17% greater risk of colorectal cancer for every 100-gram portion of red meat eaten daily. Now, one thing to bear in mind here is that most people actually don't eat 100 grams of red meat per day. It's closer to 70 grams on average. But, okay, 17%, that still seems like a big number as far as cancer is concerned. And 70 grams is quite close to 100 grams, I guess. So okay, maybe this is a significant sort of effect, right? However, we have to bear in mind that what we're dealing with here is relative risk, not absolute risk. So eating 100 grams of red meat per day increases colorectal cancer risk by 17%. But that doesn't tell you what the risk of colorectal cancer is if you eat meat. It only tells you that there's a 17% increase. Now, the average lifetime risk of developing colorectal cancer is about 4.1%. So about 4.1 in every 100 people develop colorectal cancer. So when we say that it increases by 17%, it relates to that number, that 4.1 number. It's 17% of the 4.1. So the absolute risk increase is about 17% of 4.1, which gives you, so basically it's 4.8. So to make this clear, just suppose that the studies regarding red meat and cancer risk are taken at face value. Assume that there's no methodological problems with them, the data is totally trustworthy, etc. So for people eating, diets lower in red meat, the risk of colorectal cancer is 4.1%. For people eating diets high in red meat, for people eating over 100 grams a day, the risk of colorectal cancer is 4.8%. Like if you eat an extra 100 grams a day, then your risk of colorectal cancer increases to 4.8%. So basically, by eating 100 grams of red meat a day, an extra 100 grams of red meat a day, your odds go from just over 4 in 100 to just under 5 in 100. I mean, I should say, I'm obviously simplifying. I may have gotten some of these numbers wrong, but hopefully the general point should be clear, right? So you can, again, compare that to the case of smoking. When I was talking about smoking, the figures I gave for smoking were absolute risk, not relative risk. If you're a non-smoker, then you have about a 1 in 200 chance of getting lung cancer. If you're a smoker, you have about a 1 in 5 chance of getting lung cancer. Now, that is a remarkable effect size. If we assume it's true that smoking causes cancer, that smoking causes lung cancer, this is exactly the sort of evidence we would expect to see. Or again, compare this to the effectiveness of consuming citrus fruits in order to prevent scurvy, right? Like, if you assume it's true that scurvy is caused by vitamin C deficiency, then, like, the evidence that we see is exactly what you would expect to see, right? It's like, okay, you take some people with scurvy, give them a bunch of oranges, and the scurvy clears up. And this kind of thing, well, look, I mean, it's not really what we see in the case of red meat, right? Like, we have much weaker effect sizes. And, at the very least, the causal link here is going to be much more tenuous than in these other cases. Now, to be clear, I'm not saying that red meat doesn't cause cancer. Maybe it does. And I'm not saying that the evidence doesn't support the hypothesis. Of course, the evidence does support the hypothesis. But the point is that given the hypothesis that red meat causes cancer, we would, you'd sort of initially expect to see a more significant effect size. The smaller the effect size, the more likely it is that it's due to confounding variables or biased methodologies or whatever, which we'll talk about more shortly. So, this is... Yeah, it's one issue we have here then are these small effect sizes. And bear in mind, this is one of the better cases as far as these sorts of dietary hypotheses go. I mean, as I noted, there are enough studies pointing to the link, at least a correlation between red meat and cancer, that this is taken seriously by institutions like the World Health Organization. So, this is pretty damn good. But the dietary nihilist is going to say, well, it's not that good. It's relatively good, right? But not absolutely good. We got relative goodness, not absolute goodness of evidence. Right. So this is one problem, right? We have small effect sizes. Now, not only are effect sizes small, but the other thing that you tend to find when you look at, nutrition science is a great deal of conflicting evidence. So one example of this can be found in the myriad so-called dietary paradoxes. The Australian paradox, for example, is the finding that as sugar consumption has declined in Australia, obesity has increased, which of course is contrary to all of the evidence that points to a link between sugar and obesity. The French paradox and the Maasai paradox. So this finds that French people and Maasai people have relatively low rates of cardiovascular disease despite a diet rich in saturated fats, which of course is contrary to all of the evidence that seems to show a link between saturated fats and cardiovascular disease. Then there's the Israeli paradox, which is a population with high rates of cardiovascular disease despite a diet low in saturated fats. Or consider the Prospective Rural Urban Epidemiology, or PURE study, which followed over 130,000 individuals across 18 countries. They found that saturated fat intake was not associated with cardiovascular disease, and that saturated fat intake actually had an inverse association with stroke risk. So this was reported in the article Association of Fats and Carbohydrate Intake with Cardiovascular Disease and Mortality in 18 Countries from 5 Continents. Now, of course, we can come up with explanations for these sorts of phenomena in terms of the standard dietary hypothesis, right? Like if you think that saturated fats do do cause, increased consumption of saturated fats causes cardiovascular disease. If you think that that's true, then you can come up with explanations for these findings, right? Those explanations are out there. But the point is that these findings are nevertheless unexpected given the dietary hypothesis, right? So you wouldn't expect to see the sorts of results that are reported in the Pure study if it were true that saturated fats cause cardiovascular disease. Again, you can come up with explanations, but it's just not what you would initially expect to see. So you can compare, for instance, that it's very difficult to find populations where smoking is associated with a lower risk of cancer, or where consumption of citrus fruits makes scurvy worse. Like, that's tricky to find that evidence. But this sort of conflicting evidence, when it comes to diet science, it's not so tricky to find in many, many cases. So yeah, I mean, if you're looking for, like, if we assume the truth of the hypothesis that citrus fruits are protective against scurvy, what we seem to get is just lots and lots of evidence that points in the direction of citrus fruits being protective against scurvy. But do you know what's really protective against scurvy is giving me money, because none of the people who give me money have scurvy. So you should give me money. You should go on to my Patreon, or you should just send a one-off donation on PayPal. Additionally, I offer private tutoring in philosophy. So if that is something you require, then send me an email about that. I also have a Discord that you can join if you want, and the links to all of that will be in the description. Okay then, let's turn to the prior probability of the hypothesis. So the prior probability of the hypothesis is low. So that is to say that prior to acquiring the evidence for the hypothesis, we should have a low confidence in the hypothesis. Why is this? Well, I mean, one thing, we might appeal to that kind of pessimistic induction on previous diet recommendations that, we mentioned earlier. So these sorts of dietary hypotheses tend to have a poor track record. I mean, as we noted, this doesn't in itself establish dietary nihilism, but it does mean that our prior credence in any given dietary hypothesis, our credence in the hypothesis before the evidence is in, should be relatively low. Second, as we've seen, so there are very few magic bullets, right? There are very few dietary interventions that are highly potent. And this has important consequences when we consider things like the complexity of the human metabolism. So a given food might have a small positive effect in one respect and a small negative effect in another. So, I mean, a given food might slightly improve cardiovascular health, but slightly increase the risk of colon cancer or something. This is going to make it much more difficult to give an overall assessment of its impact on health. If a food were a magic bullet, then the positive effects would overwhelm the smaller negative effects. Or maybe, the negative effects would overwhelm the positive effects, right? Like if you eat loads of Brazil nuts, that's a kind of magic bullet, but it's a magic bullet that's going to make you a lot worse off. But yeah, I mean, so for instance, let's say that increased fruit consumption, that increases the risk of tooth decay. Well, maybe, but it's more than worth it to prevent scurvy, right? Like the overall impact on health is just very clear there. So if you take a population of people who have scurvy, then you give them more fruit, maybe there's an increased risk of tooth decay, but it's more than worth it. It's much more difficult to make an assessment of things like red meat because because we're dealing with such small effects. And we're dealing with this incredibly complex system, the human body, right? Human metabolism, very, very complex. So we're just going to sort of smear out all of these like slightly positive and slightly negative effects. So this is just, again, this is just something that we should bear in mind before even looking at the evidence that's been generated, right? So any given dietary hypothesis, because there aren't any of these magic bullets, or at least it doesn't seem like there are any more magic bullets to discover, we should have less credence in any given dietary hypothesis. Another issue here is that a given food might have different effects on different people. Given the differences between people's bodies, it wouldn't be surprising if people responded differently to the same meals. And there is empirical evidence supporting this. So David Zevy et al. In the article Personalized Nutrition by Prediction of Glycemic Responses. So they monitored the glucose levels of 800 people. They found high variability in the response to identical meals. So the same meal can have highly variable effects on blood glucose. And of course, I mean, if you look at it sort of across cultures, then you might expect that to be even more pronounced. Different cultures have very different lifestyles. Like the effect of a meal is going to be very different on somebody who is highly physically active versus somebody who's more sedentary. And also, I mean, there are just some like population differences that are a product of like, genetic differences. So consider lactose tolerance in European populations relative to East Asians, right? East Asians have much more trouble with lactose intolerance. Similarly, the Inuit have appear to have specific genetics that has adapted them to a diet rich in fats. So this is reported in the article Greenlandic Inuit Show Genetic Signatures of Diet and Climate Adaptation by Fumagalli et al. And again, this isn't surprising, right? This is kind of to be expected, these sorts of differences. Another difference that we find is differences in the gut microbiome. The gut microbiome is highly variable. Identical twins share only about 1/3 of the same microbial families, but we know that the gut microbiome plays an important role in how we respond to foods. So in that Zevy article, for instance, the glycemic response to carbohydrates is linked to the gut microbiome. And what all of this suggests is, it's going to be relatively less likely that a given food will have like a regular connection to a particular health outcome. Another reason for assigning a low prior to any given dietary hypothesis might be the remarkable variety of diets that we find across the planet. So, I mean, the aim when we're giving dietary when we look at a lot of these dietary hypotheses, a lot of them are about how to avoid the sort of diseases of civilization, as it were. Things like cancer, heart disease, diabetes. We want to know, these are the primary health problems that we want to avoid. So we're looking for diets that would help us to avoid those problems. If we look at non-civilized peoples, well, they don't tend to have these diseases, and yet we find an enormous variety in their diets. And you might think, okay, well, what this suggests is just that the human body is remarkably adaptable, right? Like, provided we avoid nutritional deficiencies, provided we avoid toxicity, we can eat like a whole bunch of different things and still be very, very healthy. So take, for instance, the Hadza. The Hadza are a group of hunter-gatherers in Tanzania. Here's a graph showing what the Hadza diet looks like per month. This is from Ponce and Wood's article, Effects of Evolution, Ecology and Economy on Human Diet, Insights from Hunter-Gatherers and Other Small-Scale Societies. So, what their diet looks like is there's a lot of berries, a lot of meat, and rather surprisingly, honey. The Hadza get about 15 to 20% of their calories from honey. Some months of the year, it's about 50% of their calories just comes from honey, which they will often eat straight up. They'll just have honey as a meal in itself without even mixing it with anything. The Hadza consume higher quantities of sugar as a proportion of their calorie intake than is recommended. And yet they are not afflicted by diseases like diabetes and high blood pressure and so on. So that's one example of a diet. By contrast, the Kung Bushmen get about 1/3 to 1/2 of their calories from a single type of nut, the mongongo nut, and then a little less than that from meat, and then the rest from assorted plants like melons. The Australian Aborigines relied primarily on very lean meats with lower fat content, plus roots, seeds, fruits, nuts. The Catawba people eat a very high carb diet, mostly tubers like yam and sweet potato, plus fruits, fish and coconut. And these people, again, we don't see them developing like diabetes, hypertension, these diseases of civilization. Historically, at least, there does not seem to have been any like specific diet that is ideal for human beings. We have adapted to a wide range of environments and can eat a remarkable variety of foods. Um, and so, so like dietary hypotheses in general, um, give it. So what like okay, given the fact that human diets seem to just be highly variable, that it seems like we can be healthy eating a hell of a lot of different things. So we should be quite skeptical when somebody says, okay, this particular food has negative health outcomes, this particular food has positive outcomes. Um, okay, finally, dietary hypotheses make general claims about the impacts of specific foods, but it's likely that our classification for food obscures important complexities. So let's say that you're weighing, a vegetarian diet against an omnivorous diet. So what's the health impact of eating meat, say? Well, obviously, there are many different kinds of meat. You might look at the Inuit as an example of a high meat diet, but the Inuit eat a lot of fat and blubber. There's no reason a priori to assume that this would have the same effect as eating muscle meat. There are different animals, different parts of animals, different ways of preparing those parts. The animals have existed in different circumstances, right? Like maybe wild game that just eats wild food. That might be quite different from eating an animal that's from a factory farm where it's been fed like low quality grain. So contemporary diet recommendations focus on, okay, so we take a dietary hypothesis, a claim about, okay, this particular food has this particular effect. But the problem is that this particular food might not be a particularly useful way of classifying things, right? Maybe there's many different kinds of that food that have different effects. Now, if we look at the contemporary diet recommendations, of course, you do draw increasingly precise lines. Like, we don't talk about meat anymore. We tend to distinguish red meat as a specific thing, processed meat as a specific thing. But again, these cover a wide variety of different foods. There's a lot of things that red meat covers, a lot of things that processed meat covers. So, okay, so there are some general reasons to be doubtful of any specific dietary hypothesis, at least before the evidence comes in, right? So you should have a low prior in any given dietary hypothesis before seeing the evidence. Okay then, so finally, the expectancy of the evidence is high. Probability of the evidence is high. So what we're saying here is that the probability that we would observe the evidence favouring the hypothesis, regardless of whether the hypothesis is true, that's quite high, right? We would expect to see evidence suggesting that a dietary intervention is effective, even if that dietary intervention isn't effective. Why is this high? Well, the problem here basically comes down to questionable research methodologies and biased research. So, first of all, there are general problems that afflict a number of scientific fields these days, which you can see in the replication crisis. So this is the now rather famous fact that there are, across many fields, many apparently well-designed studies whose results just fail to replicate. And there's lots of different reasons for this. There's the publish or perish culture in academia, which incentivizes researchers to publish as much and as quickly as possible. There is publication bias, or the file draw problem, which is the tendency for journals to be more inclined to accept interesting positive results. So studies that confirm the null hypothesis, studies that find null results, tend to remain in the file drawer, as it were. So papers with statistically significant positive results are more likely to get published than those that confirm the null hypothesis, or those that fail to reject the null hypothesis. So basically, we might get numerous studies reporting apparently confirming evidence of a particular hypothesis, but then maybe there are other studies that found different results that do not support the hypothesis, but those studies were just never published, just never reported. That, of course, will create the illusion that the evidence for the hypothesis is stronger than it is. So, I mean, all of this stuff is fairly well-trodden ground. It's a problem in many academic fields, and it's a problem for nutrition science. In the case of nutrition science, there are more specific issues as well. So, I mean, one thing that's worth considering is, like, if you if you wanted to test a dietary hypothesis under ideal circumstances, what would you do? What would you ideally want to do? Well, ideally you might think, okay, you'd conduct something like a randomized controlled trial. So you take a bunch of participants, randomly assign them to two groups. One group eats red meat, the other group refrains from eating red meat. And then you control their behavior and the environment so that the only difference between the two groups is meat consumption. Since the participants were randomly assigned, any confounding variables as a result of things in, like differences in gut microbiome will also be randomly spread out. So any difference that you observe in the outcomes is almost certainly due to the different treatment, right? It's like, okay, if we find that the group that's eating meat has a significantly higher rate of colon cancer, well, that will give us good reason to think that meat is actually causing the colon cancer. I should note, incidentally, that even this kind of study would have actually quite limited application, because all it would tell you is the effect of red meat within a particular diet, right? So maybe red meat has different effects in conjunction with different foods. So, part of what it means to control this trial properly is that you make sure that everybody in both of these two groups is eating basically the same thing, where the only difference is the meat. So, but like maybe, for instance, the two groups are eating a lot of potatoes. Again, I'm just making this up, but it could be like maybe, okay, you eat red meat and a lot of potatoes, maybe that is what's causing the cancer. But if you were to have meat on a low carb diet without any potatoes, maybe there wouldn't be the cancer. That's, again, just making something up. But the point is that even if you had this kind of gold standard case, it's not obvious that you would be able to extrapolate much from it about the general population. But at the very least, you would be able to say, okay, well, we have two diets, and this diet is more likely to cause cancer than this diet. Unfortunately, randomized controlled trials are very difficult to perform. The simple fact is, we just can't get people to strictly follow diets for any long period of time. So consider, for instance, the Women's Health Initiative Dietary Modification Trial, which began in 1993, was published in 2006. Over 19,000 women were assigned to a low-fat diet where they were instructed to lower dietary fat from 38% of calories to lower than 20% of calories. Now, unfortunately, they only managed, the women in the low-fat condition only managed to lower their fat intake to, at best, 29% of their calories. And that may have been overstated. There's evidence that this was overstated because so when they were studied, they found no differences in the blood levels of cholesterol or triglycerides between the low-fat diet and the normal diet groups, which suggests that the low-fat diet group did not significantly lower their fat intake at all. So, this is a problem. So nutrition scientists will often use observational studies where we track large numbers of people who eat particular diets, gather data about the outcomes over time. But observational studies are very limited because of the wide variety of confounding factors that are difficult to control. So, for instance, people who stick to particular diets may be more likely to follow certain exercise regimens, or they may be from different socioeconomic backgrounds, or they may be more likely to, follow medication advice, or they may have different smoking histories, different alcohol use. Perhaps, they will live in different areas and so be exposed to different environmental toxins, and these sorts of confounding factors can also include other foods, because again, the effect of a given food might be dependent on what other foods you eat. Okay, so when we sort of look at a population, if we just kind of look at a population and we say, okay, well, we notice that like this population has a relatively high fat diet, this population has a relatively low fat diet, so we'll just track what happens in this population over time and see who's more likely to get cardiovascular disease. Well, the problem is that you have this huge host of other differences, a huge host of confounding factors. Now, obviously, there are methods for controlling for these confounding factors. The problem is that these methods aren't perfect, and in any case, it's extremely difficult to identify exactly what the confounding factors might be. You can, I mean, controlling for confounding factors, well, a lot of them we just might not even know about. We might not be able to control for ones that we don't even know about. Moreover, in practice, many observational studies either do not mention confounding factors or acknowledge that confounders have not been appropriately adjusted for. So Hemkins et al. In the article, Interpretation of Epidemiologic Studies very often lacked adequate consideration of confounding. They examined 120 epidemiological studies, and they found that 32 of them made no mention of confounders, 34 acknowledged that there were specific confounders that had not been adjusted for. So yes, obviously we can say, well, look, we have all of these methods for controlling for confounding factors. So that's not a problem. Yeah, in practice though, it is a problem. It remains a big problem, and sometimes it seems that even when we're aware of what the confounding factors are, scientists fail to make appropriate adjustments for them. All right, so these are just, and again, these are general problems. This isn't just a problem for nutrition science. This is a problem for observational studies in general. But when it comes to certainly when it comes to like diet and nutrition, yeah, so many possible confounding variables. It's kind of a mess. These sorts of problems are also exacerbated by the fact that the methodologies that are used are often questionable. Like, so if you consider, for instance, okay, how do we know what people are eating, right? So let's say that I want to do, some observational study where I, again, track these two populations. Well, I mean, obviously, I need to find out what these populations are eating, right? So I have one population that has a high-fat diet, another population low-fat diet. Okay, but what are they actually eating, right? What's the difference? How much fat is this one eating? How much fat is this one eating? So how do you find that out? How do you know what people are eating? Well, the standard method is to ask them. You give people things like food frequency questionnaires. So you ask people what they eat, and what the serving size usually is. Unfortunately, this is really unreliable. This does not produce good data, because people will just give unreliable reports for many, many reasons. People will forget exactly what they eat. We know that memory is unreliable in this kind of context, and yeah, so people just don't remember things correctly. People will change their eating habits just as a result of being monitored. So just keeping a diary of what you eat, even if it's only for yourself, will almost certainly change your eating habits. Like eating is no longer something you just do, it's something that you're tracking. Just try it out. Like I've kept food diaries for myself, and there is no question that my diet changes when I do that. So that's one problem. Moreover, people might just not know exactly what they're eating, right? You don't prepare every meal for yourself. You don't presumably know the exact ingredients that goes into everything you eat, especially if you get food from like restaurants and stuff. Finally, of course, people will simply lie, especially if they know that other people are looking at the diaries, right? People will just lie. And I mean, look, none of this is really speculation, right? The studies of self-report methods have shown that they generate unreliable data. So in the paper, Validity of US Nutritional Surveillance, National Health and Nutrition Examination Survey Caloric Energy Intake Data 1971 to 2010 by Archer et al. This compares people's reports of what they ate with what they would have had to have eaten in order to stay alive. And they found that the majority of respondents gave food diaries that were not physiologically plausible. So there are all of these issues with these sorts of observational studies. And just to sort of drive this point home, so in the article Deming Data and Observational Studies by Stanley Young and Alan Carr, they examined 52 claims made in observational studies that were then subsequently tested in randomized clinical trials. And in the randomized trials, 0 of the observational claims were replicated. 0 out of 52. In fact, in 5 of the trials, the opposite effect was found to what was reported in the observational study. So these are quite serious limitations. All right, a final point here is that nutrition science seems to be particularly susceptible to funding biases from the food industry. A lot of funding of academic nutrition departments comes from the food industry, and we know that studies that are funded by industry, even when attempts are made to be unbiased, will tend to have results that are favourable to industry. So in 2015, Marion Nestle examined 81 industry-funded nutrition studies over a 6-month period. Of those, 75 reported results that were in the interests of the study sponsor. Only 6 reported results against the sponsor's interests. I mean, of course, in principle, study design should be completely independent, right? Like, so you can say, well, yeah, yes, this has funding from industry, but the funding doesn't make a difference, right? Like, look, you just, the question is, like, what is the quality of the evidence? Okay, it shouldn't matter where the money comes from. It's just, has this study actually been conducted in a rigorous way, right? Is the evidence trustworthy? And you can tell that by just looking at the study and making sure that it's designed properly. Well, that's nice in principle, but in practice, apparently it doesn't work out that way. And of course, with this in mind, you might also wonder, well, okay, so if funding sources can bias research to this extent, then what about things like just ideological commitments of the researchers? Food is highly ideological, highly politicized. I mean, think about, the moral and environmental arguments against the meat industry. There are no doubt plenty of nutrition researchers who would have an interest, independently of their scientific work, in finding that meat is unhealthy. So if it seems to be the case that these sorts of biases can creep into scientific research despite what techniques we have to mitigate them. And there are many, many sources of bias here, serious sources of bias. Okay, let's summarize all of this then. So we're asking for the expectancy of the evidence, right? The independent probability of the evidence. What's the probability that there would be evidence like this, regardless of whether the hypothesis that's being tested is true? Given all of these factors, that probability is fairly high. It's high because the evidence may be a result of institutional failures, like publication bias or confounding factors, or just funding biases, whatever. Any of these factors may have been what produces the evidence rather than the truth of the hypothesis. So, if you see a study which shows that eating eggs is correlated with heart disease, that's not surprising, even if eggs don't cause heart disease. Similarly, if you see a study which shows that eggs are totally healthy and are not correlated with heart disease, that's also not surprising, even if eggs do cause heart disease. So that is the case, again, in broad brush strokes, that's the case for dietary nihilism. So let's say that you have a dietary hypothesis H, and you have some seemingly good, empirical evidence in favour of H. Unfortunately, the probability of the evidence given the hypothesis is low. The prior probability of the hypothesis is low, and the expectancy of the evidence is high. And what that means is that the probability of the hypothesis given the evidence is low. The probability of the dietary hypothesis given the evidence available is low, so we shouldn't believe it. And again, look, there are limits to this. We've already noted that there have been some striking successes in nutrition science with the identification of nutritional deficiencies. And of course, all of the problems that we've noted so far might, in principle, be overcome. Maybe these are just problems for contemporary science, but we'll figure out the solutions eventually. So you might think, yeah, okay, maybe we'd be pessimistic about the present state of things. We just need to do more science. There is one serious problem that faces dietary nihilism, but not medical nihilism. Well, maybe it's not so much a problem, but it's a concern. So dietary nihilism is an obvious propaganda tool for the food industry. If you can convince people that we have no idea what a healthy diet looks like, then that's going to encourage them to keep buying cheeseburgers and sodas, right? And I mean, this isn't speculation. You can find articles that push a dietary nihilist view that have been funded by the food industry. So we noted earlier that one reason to be skeptical of some of these dietary hypotheses in nutrition science is due to biases from food industry funding, but the same could be said for dietary nihilism. Dietary nihilism is itself susceptible to many of the problems that plague the defense of specific dietary hypotheses. And that's not, it doesn't seem like that's going to be such a problem for medical nihilism. It's less likely that medical nihilism could be a propaganda tool for industry because the medical nihilist is like skeptical of new medical interventions. They're skeptical of the effectiveness of pharmaceuticals. Medical companies aren't likely to make money off people who simply refrain from using their services, right? It's not really in the interests of medical companies to be promoting medical nihilism. Unfortunately, there's just no way to refrain from using the services of one or another part of the food industry. And it's pretty clear how dietary nihilism might well support. It might be, something that certain parts of the food industry would want to promote for reasons that have nothing to do with the concern for the truth. And so that's just one thing that you should bear in mind should you choose to go down this particular path. That is all I wanted to say today. I hope you found that interesting. And I will leave it there. Okay, bye everybody.